Back of the envelope math is a very useful tool in a system design toolbox. In this video, we'll go over how and when to use it and share some tips on using it effectively. Let's dive right in. Experienced developers use back of the envelope math to quickly sanity check a design. In these cases, absolute accuracy is not important. Usually it is good enough to get within an order of magnitude or two of the actual numbers we are looking for. For example, if the math says at our scale our web service needs to handle 1 million requests per second and each web server could only handle about 10,000 requests per second, we learn two things quickly. One, we learn we'll need a cluster of web servers with a load balancer in front of them. We'll need about 100 web servers. Another example, if the math shows that the database needs to handle about 10 queries per second at peak, it means that a single database server could handle the load for a while, and there's no need to consider sharding or caching for a while. Now let's go over some of the most popular numbers to estimate. The most useful by far is requests per second at the service level or queries per second at the database level. Let's go over the common inputs and the request per second calculations. First input is DAU, or daily active users. This number should be easy to obtain. Sometimes the only available number would be monthly active users. In that case, estimate the DAU as a percentage of the MAU. The second input is the estimate of the usage per DAU of the service we're designing for. For example, not everyone active on Twitter makes a post, so only a percentage does that. So 10 to 25% seems to be reasonable. Again, it doesn't have to be exact. Getting within an order of magnitude is usually fine. Now, the third input is a scaling factor. Usage rate for a service usually has peaks and valleys throughout the day. We need to estimate how much higher the traffic would peak compared to the average. This would reflect the estimated request per second peak where the design could potentially break. For example, for a service like Google Maps, the usage rate during commute hours could be 5 times higher than average. Another example, for a ride-sharing service like Uber, weekend nights could have twice as many riders as average. Now let's go over an example. We'll estimate the number of tweets created per second on Twitter. Note these numbers are made up and they are not official numbers from Twitter. Let's assume Twitter has 300 million MAU and 50% of the MAU use Twitter daily, so that's about 150 million DAU. Next, we estimate that about 25% of Twitter DAU make tweets, and each one on average makes 2 tweets. That is 25% times 2, so this is 0.5 tweets per DAU. For the scaling factor, we estimate that most people tweet in the morning when they get up and can't wait to share what they dream about the night before. And that spikes the tweet created per traffic to twice the average when the US East Coast wakes up, let's say. Now we have enough to calculate the peak tweets created per second. We have 150 million DAU times 0.5 tweets per DAU times 2 times scaling factor divided by 86,400 seconds in a day. Now that is roughly about 1,500 tweets created per second. Let's go over the techniques we use to simplify the calculations. First, we convert all big numbers to scientific notation. Doing math on really big numbers is very error-prone. By converting big numbers to scientific notation, part of the multiplication becomes simple addition, and division becomes subtraction. In the example above, 150 million DAU becomes 150 times 10 to the 6th, or 1.5 times 10 to the 8th. There are 86,400 seconds in a day. We round it up to 100,000 seconds, and that becomes 10 to the 5th seconds. And since it's a division, 10 to the 5th becomes 10 to the minus 5th. Next, we group all the power of 10s together, and then all the other numbers together. So the math becomes 1.5 times 0.5 times 2, and 10 to the 8 times 10 to the minus 5th, which equal to 10 to the 8 minus 5, which is 10 to the third. Putting it all together is like 1.5 times 10 to the third, or 1500. Now with practice, we should be able to convert a large number to a scientific notation in seconds. And here are some handy conversions we should memorize. As an example, we should know by heart that 10 to the 12 is a trillion, or a terabyte. And when we see a number like 50 terabyte, we should be able to convert it quickly to 50 times 10 to the 12, which is 5 times 10 to the 13th. We're going to ignore the fact that 1 kilobyte is actually 2 to the 10th bytes, or 1024 bytes, and not 1,000 bytes. We don't need that degree of accuracy for back-of-the-envelope math. Now let's wrap up by going through one last example. We'll estimate how much storage is required for storing multimedia files for tweets. We know from previous example that there are about 150 million tweets per day. Now we need an estimate on a percentage of tweets that could contain multimedia content and how large those files are on average. With our meticulous research, we estimate that 10% of tweets contain pictures, and they're about 100 kilobytes each, and 1% of all the tweets contain videos, and they're about 100 megabytes each. We further assume that the files are replicated with 3 copies each, and that Twitter will keep the media for 5 years. Now here's the math. For storing pictures, we have the following. We have 150 million tweets times 1 in 10 tweets with pictures times 100 kilobytes per picture times 400 days in a year times 5 years times 3 copies. So that turns into 1.5 times 10 to the 8th times 10 to the minus 1 times 10 to the 5th times 4 times 10 to the 2nd times 5 times 3. Again, we group the powers of 10s together. This becomes 1.5 times 4 times 5 times 3, which is 90, and 10 to the 8th minus 1 plus 5 plus 2, which is 10 to the 14th. And that becomes 9 times 10 to the 15th, which is, from the table, 9 petabytes. Now for storing videos, we take yet another shortcut. Since videos on average are 100 megabytes each, while pictures are 100 kilobytes. A video is 1,000 times bigger than a picture on average. Now second, only 1% of tweets contain a video, while pictures appear in 10% of all the tweets. So videos are 1/10 as popular. Now putting the math together, the total video storage is 1,000 times 1/10 of pictures storage, which is 100 times 9 petabytes, or 900 petabytes. In conclusion, back-of-the-envelope math is a very useful tool in our system design toolbox. Now, don't over-index on precision. Getting within an order of magnitude is usually enough to inform and validate our design. If you'd like to learn more about system design, check out our books and weekly newsletter. Please subscribe if you learned something new. Thank you so much, and we'll see you next time.